On this graph, we showed the analogy between a uniform electric field and the gravitational field on Earth. On the right, we have an object of mass m kilograms, and it is at point B, and that is lower than point A. The gravitational field is pointing down, so the gravitational force is also pointing down. If we lift the object from point B to point A, we need to do mgh of work to the mass. And by doing that, we have increased the potential energy of the mass. That is because we have pushed the object against the gravitational field. If we have thrown the ball and released it at point B, sending it up, then the speed of the object will slow down as it moves against the gravitational field. The kinetic energy will be transformed into potential energy as the ball moves up. If we take the ball at A and release it, it will fall spontaneously, and then when it has returned to point B, it will have mgh of kinetic energy. On the left, we have a uniform electric field that is pointing down. We have a positively charged particle at point B, which is lower than point A. So to move the charged particle from B to A, we will have to do work to it because we are pushing against the electrostatic force. That means that the potential energy is increasing as the positively charged particle is pushed against the electric field. If we throw the charged object, then the kinetic energy will be transformed into potential energy. Just as if we threw a ball straight up, the charged particle will slow down until it comes to a stop, and then it will start to drop, and the electrostatic potential energy will be converted into kinetic energy. So now we return to our two charged plates. On our left, we have a positively charged plate, and on the right, we have a negatively charged plate. That means the electric field is pointing to the right because that is the direction that a positively charged particle would be pushed. The work done by the electric field is the electrostatic force, which is the charge of the particle times the electric field strength. And that is then multiplied by the displacement d, which is the change in the position in the x direction. The change in the electrostatic potential energy is equal to -1 times the work done by the electrostatic force, because if the electrostatic force does work and accelerates our particle, then the potential energy will decrease. If the positively charged particle is pushed against the field, then it will gain potential energy, just like when a mass is pushed up against a gravitational field. In the opposite direction, if the charged particle is moved from A to B, the kinetic energy will increase because it is moving in the direction of the electrostatic force, and it will be accelerated, and the potential energy will decrease, just like when the mass rolls down a hill. So now we want to look at the electrostatic potential energy of a positively charged particle. So we have our plates again, with the positively charged particle on the left and the negatively charged plate on the right. So the electric field is pointing to the right. That means that the closer you are to the left plate, the positively charged plate, the higher the potential energy if the particle is positively charged. Notice the only thing that affects the potential energy is moving right and left. If we move it up and down, then we are moving perpendicular to the electric field, so no work is done by the electric field, and there is no change in the potential energy or the kinetic energy. As the object moves to the right, the electric potential energy decreases. That means if we put a positively charged particle next to the positive plate, it would accelerate to the right, and the potential energy will be converted into kinetic energy, and it will speed up. So yeah, this is just like gravity. If you want, you can tilt your head to the left, and it will look just like the gravity problem that you've done several times before. The big difference is that the positively charged particle accelerates towards the negative plate. The force depends on the amount of charge and not the mass. So as the positively charged particle moves to the left, the potential energy decreases as if it sort of rolls down the electric field. More quantitatively, the change in potential energy is equal to -q, the charge times the electric field times the displacement. Notice that if the positive particle moves in the same direction as the electric field, then the potential energy will decrease. At the same time, the kinetic energy will increase because the electric field is applying a force in the same direction that the particle is moving. So the kinetic energy increases by QE delta x. The electric force is QE, so that means we can find the change in potential energy to be the negative of the electrostatic force times displacement. And so if we graph the potential energy as a function of displacement, the negative of the slope of the line is the force. This should make sense because if we push against the force, the potential energy increases, and if we let the object move in the direction of the electrostatic force, the potential energy will decrease. Our particle will sort of roll down the potential energy curve. So the main complication that we get when we switch from gravity to electrostatics is that in gravity, there's only one direction, that is down. In electrostatics, if we switch to a negatively charged particle, then the directions of the force flips, and it goes in the opposite direction. If we have a negatively charged particle, it will experience a force pointing towards the positive plate, so it will want to move to the left. So for negative charge, the right side of the plate has the high potential energy, and the left side is the low potential energy. So our negative charge will accelerate to the left if we leave it be. Notice our equations are still correct. If we move to the right, the charge is negative, the electric field is positive, and delta x is positive. So moving to the right with a positive charge increases the potential energy, and if it moves to the left, then kinetic energy will increase. When we look at the graph of the potential energy with respect to distance, the graph flips. Now the potential energy is large to the right and low to the left. So our negative charge will roll down the potential energy curve to the left. The slope of the potential energy curve shows us that the electrostatic force is pointing to the left now. So the big trick with these questions is that you have to identify the charge of the particle. If the charge is positive, it will move with the electric field, and if it is negative, the force will point in the opposite direction of the electric field. That means that potential energy is high at the positive plate for positive particles, and it is high at the negative plate for negative particles. Okay, so you guys have a few questions to do about potential and kinetic energy in a uniform electric field. Good luck.